Okay, well, hello everybody. Welcome to the UC Center Sacramento Speaker Series. We continue with our fall series, which focuses on climate and its relation to drought, flooding, and wildfires, as well as technical innovations for solving some of California's biggest policy challenges. Remember, in winter, we'll be having a special symposium on artificial intelligence and its many ramifications for policy. But for now, we're here to talk about water, and to do that, we have distinguished Professor of Civil and Environmental Engineering from UC Davis, Professor Jay Lund. Jay is a former director of the UC Davis Center for Watershed Studies. He's a member of the National Academy of Engineering, as well as a distinguished member of the American Civil Engineers Society. He's the author of many, many, many books and reports and scientific articles, all related to water, watersheds, and the environment. But most importantly, he's really one of the few go-to people in the capital area who has developed tremendous expertise, not only in generating information that is useful for policy, but in explaining the scientific basis of those policies to both experts and non-experts. So it's always a privilege to have Professor Lund with us, and it is such a privilege again today.
Thank you very much. There's a pillar in the middle. The pillar. Thank you for coming. Those of you over here, there's pillar-free seating over here, but you can see the slides either way. So the title today is Navigating Extremes, Looking at Challenges and Opportunities for California Water Policy and Management. If you like the kind of things that I say here today, there's something called California Water Blog.com that we run out of the Center for Watershed Sciences at UC Davis, where once a week we put out a sort of a semi-scholarly but mostly written for legislative staff kind of a blog that has 14,000 subscribers. I want to talk about a lot of things today, so I'll talk fairly fast. I want to talk about variability in California's hydrology. That's sort of navigating extremes. We have a lot of variability. I'll talk about the different kinds and how it's changing. We have other things, the idea of variability and the idea of non-stationarity are kind of related. Normally, variability is a variance, it's a change that has the same structure in time, whereas non-stationarity means that the structure of that uncertainty from year to year is changing over time. And California has not only changes in climate, not only a highly variable climate, but it has non-stationarity in many other aspects of its water management as seen through history. I want to talk about some successes and failures we've had in managing what is one of the most highly variable climates in North America, and how failures, floods and droughts mostly, have led to successes, have been essential for having successes, and have led to new failures. So if you look at the history of engineering and history of problem solving, you'll see that there's a lot of attempts at successes, some successes, and every success leads to new failures. And so you're just trying to improve on the problem over time. I think for young people, that's very important to understand and to see that if it seems like we're failing now, it's only because we're living long enough to appreciate it in many cases because of successes from the past. I want to look a little bit at the outlook for this water year. This time of year, every year, people ask, is this year going to be wet or dry? Is it going to be floods or droughts? And I'm going to tell you, nobody knows until March. So don't listen to the chatter. And then I want to talk about opportunities for the future and just a couple of conclusions. So variability in California's hydrology. I came here from back east. Back east, we have 4 seasons. Here we have 2, wet and dry. And every dry season is longer than almost any drought that you've ever seen on the East Coast. So every year, California, because of its Mediterranean climate, has a worse drought than most members of Congress have ever thought about. And that's been very important. That's why our irrigation here is, our agriculture here is irrigated, and most of the United States, it's not irrigated or very minimally irrigated. Because most agriculture in the United States receives free solar desalinated seawater directly from the sky. Okay. We also have variability between wet years and dry years, not just the seasons. So we have floods and droughts. Matter of fact, we have more flood years and drought years per average year than any other part of the country. In addition to that, we have wet and dry eras. So if you go back, say, to the Middle Ages, there were periods of drought that were on the order of 150 or 200 years long. Far worse than anything we've ever seen. Far worse than anything that people usually talk about in terms of climate change for California. We've seen them in the past. Back when we were not a big agricultural or industrial civilization, or highly populous civilization. And then the last form of variability is climate change. And we certainly are seeing that now. So we have lots of variability and change in California. It's always been true, and forever it will be. So these are some aspects of the world that you're not likely to change, and this is one of them. In terms of seasonal variability, this shows the range of years. So we have the water year. Did you realize that on October 1st we had started a new water year? So happy to. The nice thing about being in this profession is we have our new years first before anybody else, before the fiscal years, before the calendar years. So October 1st is the nominal beginning of the wet season, but you can see some years it doesn't really get wet until December sometimes, or even January, like a couple of years. And it can get very wet, and up here in the Sacramento Valley, it got pretty wet last year, and it can stay pretty dry. The more recent data is very cool because you can see every day they provide the data. The earlier ones are just monthly data, and you can see each of these storms coming in. And you can sort of count these in the wet years, and you can sort of count them in the recent dry years. And you can see that the difference between a wet year and a dry year is just a dozen storms, half dozen storms. At how big they are individually and how many there are. Most of these bumps here that you see on this plot are what we call atmospheric rivers. They used to call them pineapple expresses, which I think is a more colorful name, but atmospheric river is actually a little better term because it's just a long, narrow band of precipitation that comes off the Pacific Ocean, and it's like a fire hose that hits some part of California. And depending on how many of those we have and how big each of them are, you can see the size. Some of them are really small, and some of them are really big. That's the water year, and it's only a matter of a few of those events. So this is for the Sacramento Basin. The next one is for the Tulare Basin. And I put this one up here. It's a little further south. We don't think about the Tulare Basin very much up here, but in all of California water, it is the basin that uses the most water of any hydrologic basin in California. It doesn't have the State Water Project. It has deliveries to the state from the State Water Project, things like that. So it's a little bit isolated, but it's really important. I'd say it's even the second biggest hub for moving water around in California after the Sacramento-San Joaquin Delta. And I want you to notice that in that same wet year we had last year, it was almost the wettest year on record, even though for the Sacramento Valley, it was a wet year. And it being so much wetter in the Tulare Basin, the other name for the Tulare Basin is the Tulare Lake Basin. The Tulare Lake Basin is around in about 7% of the years since all the dams went in. So it was around last year. So it wasn't it wasn't the extremist event that we've ever seen for the Tulare Basin, but it was certainly wet enough to reform part of the Tulare Lake. That's the seasonal variability. Interannual variability, you've seen a little bit of it before. I really like this plot. A lot of people use it with good reason. This is the annual coefficient of variation of precipitation at all these different precipitation stations across the United States. Does anybody here recall from your statistics classes what the coefficient of variation is? This is where I put on the Jeopardy music. Does anybody know? Somebody hiding behind the color? Do you know what the coefficient of variation is? Anybody take statistics class?
Is it a standard deviation?
It's related to the standard deviation. It's the standard deviation divided by the average. So it gives you a nice dimensionless number that indicates how much variability do you have relative to the average. And you can see, you know, I'm from Delaware out over here, where it's very boring. Move to the west, it gets a little more exciting, and it gets to California, and especially Southern California is just downright weird. We already knew California was weird. We pride ourselves in that. It's you can see it in the map. So this is where, you know, at high variance, high standard deviation, no matter what the average is, we have more flood years and drought years per average year than any other part of the country. In Delaware, almost every year is average-ish. Some variability, but not so much. This is really important because we're going to see this increase. Epoch variability. If you go back, Scott Stein got his PhD from Berkeley. He was wandering around Mono Lake up on the eastern side of the Sierras during his doctoral program, and he noticed dead tree stumps. And at the time, Mono Lake had been drawn very far down in order to provide water supply for the city of Los Angeles. So naturally, that lake was, you know, well above that level. And he wondered, how did these trees get here when the natural level of this lake in our era was much higher? And so he did carbon-14 on the tree stumps to find out how old they are. And he counted the rings to see how long they lived there. And so basically, you could deduce that from the beginning of that drought until the end, when the trees died, there had been no wet periods. So a drought that lasted however long those trees were there. And he found evidence of different droughts, some of which are on the order of 100, 200 years in length, way back in the Middle Ages and before. He also found, this is West Walker River. These are old tree stumps now in the middle of the river. You know, trees don't grow in the middle of rivers. It's too wet. So at one time, this river was dry enough for these trees to grow until the weather changed. And he found lakes along the Sierras that had been below their rims for 100 years or so. Same droughts, same really nice. And so what we did in the modeling that we do in my research group in Davis is we made a drought that was as dry and as long as these droughts. And so this is the Haru paper, Water Resources Research 2010. And you can see on the right-hand side of these that, get my cursor back. Oh no. You'll see that the lower line on the right-hand side, your right-hand side, that's the trace we had for the drought, and the other is the historic hydrology. You will notice one thing from this drought. It doesn't matter how big your reservoirs are, you won't be refilling them because there are no wet years. I often talked about how we need to build new storage for the climate change. Not always, sometimes it's just wasted money. Okay, so climate change. We have this other non-stationarity that's occurring in addition to this huge amount of variance that we have. Higher temperatures, the biggest thing with climate change. So it's going to have increased evaporation rates, evapotranspiration rates, has less snowpack. More of the annual runoff is going to occur in the winter because the precipitation will fall as rain and not snow. Also because it's not falling as snow, it'll run off in the winter, and it won't be around for spring snowmelt. Less spring snowmelt and less summer floods. That means the fire seasons are longer. It means you drain some of the groundwater seasonally quicker. Longer fire seasons. We'll have greater precipitation variability. So in a warmer climate, the atmosphere can carry more moisture, more density of moisture. And then when it hits the mountains, it'll fall out at a faster rate. So that can make the floods happen more easily. So we should expect to see the floods worsen. Because of the greater evaporation, you have an additional water consumption use from whatever precipitation that occurred. So the same amount of precipitation gives you less runoff because the temperatures are higher. So it makes small droughts into worse droughts. It makes smaller floods into bigger floods. In addition to that, the higher temperatures and the other things will be changing the ranges of native and non-native species. So we can expect more non-native species invasions and it to be harder to maintain native species in California. Farmers also, they're in a global market for their products. They'll be trying to change the varieties of their crops and the types of their crops to be better suited to be productive in this climate, in this changing climate. In addition to that, another artifact of higher temperatures at the global scale is the oceans will be expanding. So water expands just a little bit when you warm it up, and if you have miles of ocean, it expands a lot. So the oceans will have the same mass, similar mass, say, but bigger volume. So sea level is rising. This has issues for many of our coastal areas and certainly has issues for the Sacramento-San Joaquin Delta. Overall, California's climate is becoming more like California's climate, having high variability going to higher variability, and becoming a little drier on that. Strategies for managing extremes. So California is already very well practiced with managing extremes. We're just going to have more of it to manage. What are the strategies to manage hydrologic extremes? What can you do? You can store water. Okay. People say, okay, we got to build reservoirs, we got to put water in groundwater. Those are all good things. What other strategies can you have when there's greater variability? What do you do when your income is variable? Students here are used to having variable incomes. You store much of it? You can't store very much of it. Your income is pretty low. It's hard to store it, although you do some. You can reduce your demands. Okay. Students tend to have old cars. I had really old cars when I was a student. So you can have reductions in demands. In our case, permanent reductions in water demand. So I think we'll be seeing quite a lot of that. And counter-cyclical management of demand. So when it's drier, use less water. When it's wetter, use more water. You can use more water because it's more available. It's not rocket science, but it's how you make a water system that works. The third thing you can do is you can try to add supplies. You can add a permanent supply, either permanent water imports, or maybe you have a desalination plant that you only run during droughts. That's very expensive, so I wouldn't recommend that. But that's the kind of thing you could do for a permanent supply or for a drought supply. We've done a lot of this in the history of California. The southern part of the state has imported a lot of water from the northern part of the state as a way of accommodating the high variability in Southern California. So this is very much like managing household finances. You can manage the variability with savings, expenses, and income. Same idea. Like I said, it's not rocket science. However, they all cost something. If you borrow money, it costs you something. If you build a reservoir, it costs you something. If you put water into a reservoir, you don't get interest on it like you would in a bank account. You lose water because of evaporation. So in this hydrology, in this big, very diverse state, we have a lot of complexity in water management. So just to give you a spatial sense for water management, I like this map here where the dark blue is 20% of the surface area of the state that provides 2/3 of all the runoff, of all the water. Light blue is another the next 20% of the surface area provides 24% of the water. Where is this darker area? Where is this bluish area? Is it scattered randomly around the state? It's up north. It's up where we are. We control the water. That big red area is 30% of the surface area of the state. The runoff from that area is 0.1%. In between, we have another 30%. So where do we grow? Where are the cities? Well, San Francisco is a pretty wet area. Sacramento is not too dry. Fresno is really dry. Los Angeles area, not a lot of water down there. So they import a lot of water. They have to go pretty far, as you can see from that map, to get water to import. They're not going to get much from that red area. Those demands also are in the summertime, and the water is available in the wintertime. So we have this tremendous time and space imbalance in where we have water and where we like it. So California is just a wonderful place for civil and water engineers. And that's the map to the right. We build lots of dams to move water in time. We manage aquifers to move the water in time. We build lots of canals, pumping plants, all things like that to move water in space. It's all about time, all about space. And I have a little cartoonish map there of Massachusetts, just so you can see how big this system is. The system for Boston, which is over to the eastern side of Massachusetts, gets water from western part of Massachusetts, and they have an aqueduct that goes across most of that area. And that's much shorter than Hetch Hetchy. And that's the biggest thing in all of Massachusetts. The other thing about the map to the right is it's kind of colorful. You'll see state projects, federal projects, and lots of local projects. Most water provided in California is provided by local projects. That ownership and that control colorfulness is reflected in how colorful the politics and the management of the system. There's a wonderful saying I like that in the United States, we hate government so much we have thousands of them. It certainly holds true in water. We have about 3,000 local water districts, and then each state and the feds have about a dozen state and federal agencies that have something to do with water. So we have the State Water Board as well as the Department of Water Resources and Department of Fish and Wildlife and other agencies. So we have a lot of decentralization. We talk a lot about groundwater these days, as well we should. We have the Sustainable Groundwater Management Act. For decades and decades, we've overdrafted about 2 million acre feet per year in the state. Over the last 100 years or so, we have overdrafted about 120 million acre feet in the Central Valley alone. If you take a top-down view of California water, you see the map to the left that you've already seen. The total surface storage capacity of all the reservoirs in California is about 42 million acre feet. The The map to the right is a bottom-up, looking from the center of the earth up at the water infrastructure of California. And you'll see there's about 150 million acre-feet of aquifer storage. So most of storage in groundwater, particularly for droughts, is groundwater. And this will always be true. And it has already been built, and it already exists. And you don't have to pay to have it built. You have to pay to pump water out of it. You might have to pay for the water that you're going to let recharge into it, but the storage itself is already built. Just to drive that point home a little bit, here's a little bar graph that shows the total capacity of water storage, as underground capacity, and surface water storage, and then sort of the normal amounts of use, seasonal storage, so within the average year. For groundwater, we use surface water a little bit more for seasonal storage, but we use groundwater much more for drought use. But we do a fair bit of it seasonally as well. And that's we're next to the Capitol. We have a lot of people talk about building new reservoirs. If you took all the proposed reservoirs, and there was a Proposition 2 or something like that, $2 billion, set aside $2 billion of money to build new reservoirs in California. If you build them all, that's how much new storage you get. There's a rule of thumb that it takes about 7 acre-foot of new storage to get 1 acre-foot per year of new water deliveries. It's very approximate, but it gives you a sense about what you're working up against. It's very expensive to build that storage, and you don't get a lot of water from it. Why is that? Because all the best reservoir locations already have reservoirs. They were the cheapest to build. They had the biggest rivers flowing through them. You've reached the site capacity for many of those reservoirs, so it gets really expensive to do it further. Non-stationarity in many forms. We've got a lot of different forms. Climate, changes in water use. The biggest changes we have seen in water management have been with changes in economic structure over this history of California. When we moved from a mining economy to an agricultural economy, to an industrial economy, to a service economy. Those have very big changes. If we were still an agricultural economy with maybe 40% of our GDP coming from agriculture, and we had a drought like we've had recently, it would be completely devastating. Today, maybe 3 or 4% of the state's GDP is agriculture, but agriculture is 80% of the water use. So the changes in economic structure, I would argue, have been our best drought management strategy. Even though we didn't have to do anything particularly about it, we just had to get rich. To me, the most difficult non-stationarity we're going to face is the non-stationarity of ecosystems. We're here in Sacramento. State and federal policy on the ecosystem is trying to prevent change. We don't want to see species extinction. We want to see the same ecosystems that we had in the 1800s. We're having trouble getting that to work. We're going to have more troubles getting that to work as the temperatures rise. You can all understand how ecosystems change when the ambient temperatures change. So we're going to have even more trouble going back to ecosystems that we had in the past. I would like to go back there. I like salmon as much as anybody, but I'm just saying, scientifically, that it's going to be harder and harder to go back. Eventually, we might decide we can't go back. I think you could make a compelling argument that says you actually cannot go back. Sociologically, politically, it's easy to decide you want to go back to what you had in the past. We have some politicians that make that into their main slogan. But we don't have a choice of going back. We have to go forward. But when you're going to go forward, you have to decide, well, do I want to go this way or that way? That's a really difficult thing to do. And I think it's the kind of questions and kind of line of discussion that we should be cultivating at the University of California, because It's going to take decades to see that conversation come to some relative consensus. I don't think it'll be great consensus, but it's really necessary because that's the weakest part of our water system, is ability to provide for ecosystems. We also have accumulating nitrate contamination in salts and aquifers, and we still have some accumulating aquifer overdraft, although our Sustainable Groundwater Management Act is supposed to end all that by 2040, and I'm sure that's going to happen. We also have non-stationarity in our societies. Our societies are aging, they're becoming more heterogeneous demographically in all ways, and we have trends in what we think of are social objectives, particularly things like social justice and the like. So as water managers, as water policymakers, we have to manage with all these forms of non-stationarity. We can't do just climate change because climate change is going to be working with all of these other forms of change. We have some nice things that have been happening. Reduced urban water use. So it's very easy in Sacramento to talk to people and say, well, we should reduce urban water use, but urban water use is only 20% of human water use in the state. Fortunately, it's been going down particularly motivated by a series of droughts. We use basically half of what we did 30 years ago in terms of per capita. We have a little more capita, but we're also reaching the point where we're having either constant or maybe even slowly declining total population in California and many parts of the world, actually. Another change that's really important is, again, the economic structure of agriculture in the state. You can see a growing percentage of orchards in the state. So basically a third of the state's croplands, irrigated croplands, are permanent crops, orchards. They bring in a lot of money. They use maybe a little bit more water than the crops they replace per acre, but they make a lot more money per acre. So if your objective is to try to reduce rural poverty, I think it's a good thing. If you want to have more rural poverty, insist that California not export anything, that we only eat what we grow. That's a good way to make rural areas poor. I'll put that idea to rest. Groundwater overdraft and contamination. We have millions of acres of land that we've been applying nitrate to, nitrogen fertilizers to for 100 years, roughly. It's still going up. Eventually, that nitrogen becomes nitrate, which is a contaminant, acute contaminant for drinking water. So rural areas of the state, and this applies to any rural area that has a lot of nitrogen-based agriculture, you wouldn't want to drink the water. And out in rural areas, it's hard to fix because they don't have much economy of scale. So I want to reflect a little bit on successes and failures. We've got a lot of successes we've had with human water problems. So I put them on the top. Those are in green. Agriculture has been a big success, but it's also a weak point because it uses so much water. Rural drinking water, largely because of nitrogen contamination and some overdraft, a lot of the overdraft has a hard time, relative failures there. Ecosystems, I think, have been largely failures. We've had more success on the environment side for waterfowl. So we have a pretty good system of waterfowl management and wetlands management for migratory waterfowl. But on the fish side, we haven't figured out how to be successful yet. This is globally number of deaths by risk factor. And what I want to point out here is we still have sizable public health aspects of water problems, a few in California, but more other parts of the world. But from a public health perspective, the biggest problems we have is what we eat and breathe, at least from this data source. So be careful what you eat and what you breathe. I mentioned the problem of non-stationarity for ecosystems too, unavoidable non-stationarity. Basically, we've multiplied and subdued the earth. Now what? We're seeing the problems of that. How do you go back? Can you go back to pristine nature? Maybe in a few places. Probably not perfectly. Can you do something like ecosystem reconciliation? It's a nice buzzword. It's the idea of, since most of the Earth's surface we manage for human purposes, how about we manage those for human purposes, but adjust them a little bit so it's friendlier to the kind of ecosystems we want to have. We might get more ecosystem benefit out of that than adding a few percent to pristine reserves. And then in Europe, when I go to the Netherlands, they talk about nature a lot, but they mean nature a lot differently than we do. Here we talk about endangered species and things like that. There they talk about having stuff that's green, having some kind of an ecosystem, not being too particular about the species. It's something that's not concrete. Probably we will have to have some sort of a diverse and adaptable portfolio of different kinds of ecosystems that we're going to make, but deciding on those will be a problem. There's a lot of things we can do to manage water for any of the purposes. I won't belabor it, but we have a very rich toolbox. But using each tool costs some money and requires some organization. And they can work across large spatial scales as well as small spatial scales. Where we've had successes, we've created new failures. If you look at the history of California water, it's a history of failures and adaptations following failure. So every flood, every drought brings failures, forces us as a society, as a profession, to work on those failures. And so if you look at the history of innovation in the water field in California, it's driven by floods, droughts, and lawsuits. And we have so many floods and droughts, we have a greater frequency of innovation than most other parts of the world. And so that's part of our success, is we've had a lot of failures. How many of you learn more from tests that you do poorly on? Same thing. We're going to have a lot of forced opportunities from all this non-stationarity and variability. Some of the big things I think are making sure we implement Sigma well, reduce irrigated area in California by about 1 to 2 million acres. We have to reduce it by 1 million acres on that order in order to accommodate Sigma. And then we have climate change and the other things we want to accomplish. We're going to have to rescope for more our management make ecosystem management more effective. And because we're always going to have a very mixed system of lots of different purposes, natural and human, we're going to have to look for a lot of opportunities for multiple benefits. We have a lot of reasons for pessimism and for optimism, but I think the bottom line I have is always become an optimist, because pessimism is always self-fulfilling. The nice thing about working with students is you can have them work on projects and they don't know it can't be done. Whereas if you go to an agency or a normal consulting firm, they'll say, oh, that can't be done. You shouldn't even try. But sometimes that's where real progress comes, is when other people thought it couldn't be done. Outlook for this year. Great reservoir storage. Almost everything's full. Wonderful. Groundwater storage is better than it was the year before, but it's still quite depleted. Precipitation forecast, I say, ha, ha, ha. Nobody knows this time. There's almost no correlation between precipitation last year and precipitation this year. El Nino, people talk about El Nino. You've probably all heard about El Nino, people saying, oh, it's an El Nino year, it's going to be wet or dry. There's the correlation for you. This is your citizen science exercise. Look at that plot of El Nino Southern Oscillation Average Index versus water year flow from the Sacramento Valley. How much should you be paying attention to El Nino? Don't just think about other things. Be more productive. However, because the reservoirs are full, last year when the big storms came in, the reservoirs were empty. It was really nice. We didn't have to worry about floods as much. On local tributaries, we had some floods, we had some deaths. It's terrible, but the big systems, that's how these reservoirs are full. So we're going to have to worry more about floods. And if the coming year is dry, we're probably mostly okay because we have good reservoir storage now. I'll put a plug in for this website for looking at the state of the reservoirs. Oh, this just shows that, boy, that's the slowest 5 minutes I've ever had. Still have 3 minutes left. Thank you. You'll see from this plot that about 85 to 90% of all the crop revenues and agricultural employment is from half of the irrigated acres. I mentioned we're going to have to lose 1 or 2 million acres of irrigated land. Which do you think the farmers are going to follow? The stuff that makes money or the stuff that doesn't make as much money? They'll be sad because they're not making as much money, but they'll still be a very large and successful agricultural economy in California. My last slide. Resistance is futile. Are there people here? Am I old enough now that this reference is too dated? Anybody, any non-Star Trek fans? The board, cube? Oh no, that's a bad sign. All right. You know, okay, so some of you know it. Explain it to the others. We're going to see changes in California. They're unavoidable, in all different aspects. California's water has always changed as the economic structure has changed, as the technologies we've used have changed. It's going to continue to change. We need to accept some of these changes and implement them in a better way for a better future. And then because I'm a professor, here's some readings. Thank you very much.
Thank you so much, Dr. Lund, for a great presentation and talk today. And so we are going to take questions. And our first question we'll go ahead and take from the audience, in-person audience.